So, just a reminder, everyone is on mute. If you'd like to ask questions, you can use the chat box, and we'll answer as many questions as we can when we're done. We are recording this webinar, and it will be available on our YouTube channel either later tonight or tomorrow morning. Yesterday's webinar was posted last night. So with that, we'll get started, and I believe Rodney will lead us off.
Well, thank you, Joe. So if you were to remember, leading up to this flooding event, the middle of May was a spectacular stretch of spring weather, mostly dry and cool conditions. And Joe, next slide, please. And the reason for that was we had a kind of a Rex block pattern, and what that means is that we had a kind of an upper level ridge from the Central Plains building over a closed off low over the Ohio River Valley. And you might remember there was unfortunately devastating flooding in Michigan. Some places got like 8 to 10 inches of rain in a week, but we were kind of left high and dry. And when you get into that kind of upper level pattern, it is very persistent. And for days we had cool spring weather thanks to a northeast flow of the ocean. But because the air is so dry, there wasn't really any marine low stratus along the coast. But anyway, so the reason why we talked about this was that because it was so persistent, and then now finally there's a pattern change, and the upper level low moved east closer to our area. And so leading up to this event, there was a lot of disagreement in the model guidance where the heaviest rain would fall. Most of the guidance put it south of the Mass Pike, which kind of makes sense because as the surface low moved in from the Mid-Atlantic region, there would also be a high pressure building in from Canada. So that kind of that means that there would be a pretty narrow zone of rainfall, and the question is how much rain is going to fall. And when we use a blend of guidance, then that is to take different model output. We got about 0.5 to 0.75 inches of rain. The other parameter we looked at is precipitable water to see how much moisture we can get out from the atmosphere. And we saw pretty high PWatt values of 1.25 to 1.5 inches, and we will talk more about that later. And so this is the surface map on the day itself. On the left-hand side, that's at 8 a.m. on Saturday morning. You can see a cold front to our north and a surface low just south of New York City. And that is the low pressure that I talked about earlier that was kind of over Ohio River Valley for days, and then now it finally moved east. And so the question becomes, how much rain can we get before the cold front from the north builds south? And then looking on the right-hand side, that's 3 hours later at 11 a.m. And you can see the cold front has advanced further south, but then also the low pressure has moved further closer to our area, kind of just south of Nantucket. And that would be the kind of north of the low pressure, that would be the area of focus for the heavy rain for this event. So we talked about, the blend of guidance that's looking at different models. But we also look at ensemble, and a lot of you would be familiar with models like GFS, the NAM, the European, and a lot of times when you look at these models on websites, commercial websites, they give you a QPF amount. That's a deterministic guidance. but in order to get more confidence in the output, we look at ensemble, not just, and in this case, you know, the GFS, the ensemble equivalent is called the GEFS, Global Ensemble Forecast System, and it has 21 different members, and in the next couple of slides, I'll show you how you can look at the different output from the different members, and those are called plumes or spaghetti plots. On the left-hand side is the Jeffs GEFS plume for Nantucket, and you can see this is a pretty wide range of outcomes, as low as 0.7 of an inch, as high as 1.8 inches. And then if you take the kind of the mean of the 21 different members, you get about 1.2 inches. And that's for you know, the 6Z cycle. 6 hours later, you see that the members kind of trended downward. And when we, as forecasters, we look for trends, and in this case, we would have a little bit more confidence in kind of like a lower QPF outcome based on the trends in the downward trend of the QPF by the different members. And this is the SREF. So both the GFS and the SREF are produced by NCEP, National Centers for Environmental Prediction. And the SREF stands for Short Range Ensemble Forecast. And for those of you who are not familiar with SREF, it is a short-term guidance going out to 87 hours. Also has 21 members, runs 4 times a day. And this, because it's short range, in this case, we looked at this and try to see how much QPF it gives us. And what we see here is, so on the top, that's the output from the 22nd. So that's Friday, and you can see most of the members are kind of like clustered around 0.5 inches. The mean is actually less than that. But with a later run, at the bottom, you can see that the members actually, there's a wider spread. And not only is the mean higher, the outliers in this case show above 3 inches of QPF. And that's actually a red flag. And you know, going forward, you will see how this SREF would kind of lead us to kind of trend to up our forecast in pretty short notice. So talking about the high resolution model performance, you know, we show you the GFS, the GFs, and then we show you the SREF, the short range guidance. And clearly the short range guidance, because they are higher res, they provide more details for events within 36 to 48 hours. And also they use different physics to better simulate the atmospheric processes, and they are more skillful for smaller scale events, as I've alluded to, because it's kind of localized, and they tend to do better to produce more realistic outcomes. In this case, it is the QPF amounts that we are interested in. So I will pass it on to the next presenter to talk about the HREF ensemble guidance.
All right, thank you, Rodney. This is Frank Nocera. So yeah, as Rodney was covering the GFS ensembles and the SREF short range ensembles, we're going to look at the HREF, the high resolution ensemble forecast. These ensembles are higher resolution than even what Rodney was showing. The GFS ensembles are roughly 34 kilometer resolution, so every grid point is spaced about 34 kilometers in between The Schreff is even a greater distance, about 40 kilometers in between grid points. The HREF here that we're looking at, it's composed of 5 different members, the Nessel-Whorf, the NAM-NES, the HER, the ARW, and the NMM. Each of those 5 models, the grid resolution is about 2 to 3 kilometers grid spacing. So you could see how these short-range ensemble models here have a better chance of picking up on mesoscale, very narrow rain bands, where the GFS ensembles and the Schreff the grid points are further apart, so they would have a tougher time simulating narrow rain bands. So we probably have a better shot of seeing those mesoscale rain bands with the HREF. So what we're looking at here is the 6-hour mean QPF from the HREF, and this model was run at about 8 p.m. the night before. So this is really the last set of guidance that forecasters would have been able to look at before the event. And the event, again, was on the 23rd, roughly between 8 a.m. and 2 p.m. So this version of the HREF, again, this is the 6-hour QPF rainfall, the mean of all 5 of those members from roughly 8 a.m. on Saturday to 2 p.m. on Saturday. And you could see how in this time frame, this model is showing you that the heaviest rain is actually going to stay to the southwest of southern New England. Heavy rain across Connecticut, Long Island, maybe into Block Island, but as far as Martha's Vineyard, Nantucket, and southeast Massachusetts, it's really a struggle to get heavy rain into that area. But again, not too far away to the west, we have some heavy rain, and the mean is showing you about up to 2 inches of rain in coastal Connecticut area there. On the next slide, we'll look at the heaviest member of these 5, and actually it's 10 members, the HREF. The HREF is those 5 members I was telling you about, the Nessel-Whorf, the NAM-NES, the HER, the ARW, and the NMM, plus the previous run of those 5 members. So it's really a collection of 10 ensemble members. So out of those 10, this was the wettest, heaviest member that we're looking at right now. So this is the most rainfall that any of those 10 members had from 8 a.m. Saturday to 2 p.m. Saturday. You could see really not much different than the mean. The heaviest rain is still off to the west across Long Island Sound, coastal Connecticut, and some of those reds are indicating 3 to 4 inches of rain, but no 3 to 4 inch amounts near Martha's Vineyard and Nantucket. Now, for those of us that forecast for a living, we know when we see these tight gradients, it's really kind of like the kiss of death to forecasting. Bad things usually happen along gradients, and it's really, really tough. So here the model is indicating, yeah, that parts of coastal Connecticut, Long Island Sound, maybe even Long Island could have 3 to 4 inches of rain. But how much of that do we believe could go further to the northeast, further to the southwest? So that was one of the dilemmas with this forecast. Some of the models were hinting heavy rain not too far out to the west, but just where would this boundary have this boundary of heavy rain? How close would it come to southern New England? All right, so let's take a look at the analysis and some more data, try to put the pieces together to see here what exactly happened. So we're looking here at the surface map at 11 a.m. on Saturday morning, and you can see by the wind barbs we have northeast flow across most of Massachusetts, Connecticut, Rhode Island, but as you get down to Martha's Vineyard and Nantucket, the winds have just turned to the north-northeast, so we had a backdoor front coming across the area, and the wind shift just occurred at about 15 Z, but you can see we're still kind of in the warm sector for Martha's Vineyard and Nantucket. Dew points are 63, 65, and keep in mind this is May 23rd. This is not June or July, so dew points in the mid-60s. It's a pretty moist air mass. But notice what a sharp front this is. If you go up to the north in northern Massachusetts, around the Fitchburg area, dew points drop into the upper 20s, and even across the border there in Manchester at 28 dew points. So over a very short distance from northern Mass to southern Massachusetts, the south coast, you go from dew points in the upper 20s to mid-60s. That's really a sharp gradient, a sharp boundary. And that boundary did contribute to the heavy rain, but we'll see in later slides that there was even other contributions for the heavy rain over Martha's Vineyard and Nantucket. So moving forward 3 hours later to 2 p.m. on Saturday, you can see now the backdoor front has blasted through Martha's Vineyard and Nantucket. Their dew points went from the mid-60s now to the low and mid 50s in just 3 hours, and the front is even now heading into Long Island. So we're now on the cool side of the boundary, but if you notice at Martha's Vineyard, it's still raining, even New Bedford and Falmouth. So we're still even getting rain on the cool side of the boundary now. So interesting setup here. On the next slide, we'll look at the hourly observations from Martha's Vineyard. So at the top, we have the 1148Z observation, and then at the bottom is the 1753Z observation. So it's in chronological order. 1148Z, that's 7:48 a.m. in the morning. I had the privilege of working this day, so this was a pretty challenging event that I remember. One of the first clues to the event that day was at 12:53Z, which is 8:53Z. About a half inch of rain fell in that hour at Martha's Vineyard. Not enough rain for flooding, but enough to get our attention. And then at the next hour, we had about 4,300, so almost an inch of rain in the past 2 hours. Again, not enough for flooding, but when we were looking at radar and satellite, the trends, were pointing towards even additional rainfall. And I believe the flood warning went out at about 10:15 or 10:30. So shortly after 1 inch of rain had fallen, we went with a flood warning for Martha's Vineyard and Nantucket. If we go down to the 17Z ob there, 1653Z, you can see they had about just over 0.8 of an inch of rain in that hour. And then at 18Z at 2 p.m., the 6-hour total was just over 2.5 inches of rain. And I think certain parts of Martha's Vineyard you'll see in a later slide had almost 4 inches of rain. So this was right here at the airport, but even higher totals were observed in other parts of the island. So pretty impressive for 6 hours. Again, there was about 4 inches, 3 to 4 inches of rain. So let's take a look. We looked at the weather at the surface, what the weather maps look like. Let's take a look at about 10,000 feet, 700 millibars, and see what was taking place there. So the image to the left is the 700 millibar height contours and wind contours, and then the green hashed areas where relative humidity meets or exceeds 70%. So where you see the green hashed area, you could expect clouds, moisture, and precip in that area. So the left image is at 14Z, which is roughly 10 a.m., and then the image to the right is 19Z, so that's 3 p.m. So 10 a.m., 3 p.m. So one of the things you want to look at that kind of jumps out to us is if you look at the wind barbs around Nantucket and Martha's Vineyard, you have southerly flow there, approaching the islands, but then the flow just to the north of the islands is kind of from the west-southwest. So you actually have converging air. You have air piling up there. And when you have converging air piling up, it rises. And if you have upward vertical motion, if you're lifting moist air, you're going to have clouds and precipitation. Looking at the right image here at 3 p.m., much of the same. South of the islands, you have southeast winds, and then to the north of the island, you have light, even northeast flow. So again, converging air piling up, it's going to rise. If you're lifting moist, saturated air, it's really a good setup for precipitation. The next slide, we'll move down to about 5,000 feet, 850 millibars. And what I want point your attention to, same time frame to the left, 14Z, and then to the right, we're looking at 19Z. So again, 10 a.m. to the left, 3 p.m. to the right. If you look at the green contours, this is what's significant here. These are contours of dew point. So this is how much moisture is at this level of 5,000 feet. What's important to note is that how tightly packed these green contours are, and that's because we have converging air even at 5,000 feet. So we're looking at a boundary here, a moisture boundary, and if you look from the 10 a.m. picture on the left to 3 p.m. on the right, this boundary isn't moving very much. So if we have a rain band set up, we could expect it to not move very much. It doesn't have to rain extremely heavy, but if it's there 10 a.m. to 3 p.m., you're looking at 5 hours of a stationary rain band. Next slide, I think we go down to 925 millibars, which is roughly 3,000 feet. Same signature here. We have tightly packed dew point contours. So this is a pretty deep boundary. We saw it at 700, 850, and now at 925. So we have a deep boundary, stationary, really a good setup for some heavy precipitation. Here is another map just showing you moisture content, precipitable waters, abbreviated as PWAT. The image to the upper left is 15Z, so that's 11 a.m. To the upper right is 18Z, 2 p.m. And then the lower image is 21Z at 5 p.m. So the shaded area is showing you high moisture content. Precipitable water is actually giving you a measure of not how much moisture is just at the surface, but through the entire column. So from the surface up to like 20, 30,000 feet. So especially the dark green areas, that's really a high concentration of moisture. And you can see those vectors, those arrows, they're pointing those higher values. They're advecting them, transporting them towards Nantucket and the islands at 14Z, at 18Z, and even at 21Z. And those arrows, they're converging, and that's why we're noticing in this loop here from 15Z to 21Z, we have that sharp moisture gradient just remaining stationary. So that's pretty troublesome. And again, those values were about 1.6 right near Nantucket and Martha's Vineyard. So to put that into context, you know, what is a precipitable water of 1.6 at the end of May? Is that high? Is that low? Is that average? Well, the Storm Prediction Center has a sounding climatology for all the weather balloons that we launch out in Chatham and all the other locations across the country. But we'll just look at here at Chatham, Massachusetts, where we launch the weather balloons twice a day, roughly 7 a.m. and 7 p.m. So that value on the meso-analysis showed precipitable waters of about 1.6 over the islands. Well, where does that fall from May 23rd, where that black arrow is? That is the record precipitable waters for the date. And at the lower right-hand corner of the, you can see at the bottom there, the text, the max moving average for the day is 1.67. The balloon launch and the meso-analysis are indicating almost 1.6 inches. So that tells us that we have almost a record air mass, moist air mass in place. That's really setting the stage for the potential for some heavy rain here. So very moist, almost record-breaking moist air mass for the date. Something else that came into play that's a little bit complicated, I'll try to keep it as simple as possible, something we call warm rain processes. Another way to think of it too is like high precipitation efficiency. So was the atmosphere set up for very efficient high precipitation? So the image on the left is the sounding, what the weather balloon launch looked like at 8 a.m. or 7 a.m. that morning of the flood event on the 23rd. And the image to the right is the Brookhaven sounding from central Long Island. So the red curve, for those of you that aren't familiar with soundings, the red curve is the temperature curve, the green curve is the dew point curve. So the closer those two curves are together, you have higher moisture saturated environment. Where the curves have more distance between the two of them, that's where you have some dry air. Well, both of these are pretty saturated for this time of year. And some of the things that we look at to give us clues to check if there is warm rain processes possibly happening is the depth of the warm cloud layer. So, Joe, if you could just point out the LCL on the Chatham sounding, even shows you there, and it's actually labeled in brown. Yeah, right there. The LCL, which is the lifted condensation level, that's about the height where you would get, if you lifted moisture or a parcel at the surface and lifted up, you would get clouds to form. So obviously it's very moist. You don't have to lift an air parcel too far. It's about maybe 500 feet above the ground level. That's where your LCL is. So the definition of warm rain processes is the distance from your LCL to the -10. And then, Joe, if you just want to look where the -10 is, it's up around maybe 5 kilometers off the ground there. So your depth of your warm cloud layer is about 4.5 kilometers. So that meets the criteria for a warm cloud depth. And what's important about that, about having a warm cloud layer, is the probability of having hail in that environment is very, very low. So if the probability of having hail in this environment is low, you're not going to lose any water droplets to hail production. So all those water droplets could go into heavy rain. So that's one of the important factors about heavy rain processes. The other important thing that jumps out here is that kind of like that dashed line, if you want to show, Joe, that shows how buoyant the atmosphere is. Some of you may have heard the word CAPE, buoyancy. Well, that looks like, to us, we label that as kind of a long, skinny CAPE profile. And that also tells us that this atmosphere, this setup is not really conducive to like vigorous updrafts. We're going to have weaker updrafts. And if we have weaker updrafts, that's going to contribute more to heavy rain, where if you had vigorous updrafts, if you had short, fat cape, it would be more conducive to vigorous updrafts, and then you may get some hail production, and the hail production is going to take water droplets away from the heavy rain and to produce the hail. So another criteria for the warm rain processes. And probably the last point I'll point out here, I know we're throwing a lot at you, and feel free to ask questions at the end, but notice the winds from the surface all the way up to 500 millibars, even 300 millibars are very weak. You basically have 20 knots wind at 500 millibars. That's not a lot of wind, especially for late May. That's very light wind. And by having light winds throughout the column, there's less chance that you're going to entrain or advect or bring in dry air from other nearby sources into the column. So good chance that this moist column of air is going to stay saturated because you're not going to be advecting in any drier air from other regions. And what's typical with that setup, we didn't even have any lightning with this, so it's kind of a little deceiving where, you know, where you maybe be expecting lightning, your cloud tops are cooling, but you're not seeing any lightning. So we'll pass that on now to what happened. I think Bill Leatham is going to take over and talk about what happened for the event.
Yeah, thanks, Frank. All right, so what we've got here is a radar loop from the Boston radar. Luckily, the radar did come back up online after that upgrade that we had. But it's just a radar loop zoomed in on Cape Cod and the islands. And as folks can see, the big thing that we call in these kind of scenarios is that the storms were training over an area, and what that essentially means is that the storms are just concentrated over the same area, or they're just kind of stationary. And as you can see here, the Martha's Vineyard and Nantucket just continued to see rainfall falling over the area, and this was over a couple hours. I think it started. It ends at about 21 or closer to, into the evening, around 8 p.m. where you can see all the rain moving away. And it started, I think, at about 10 a.m. is when, or a little before 10 a.m. But the rain really didn't start getting going until about 8 a.m. If you want to go to the next slide, Joe. And so this is one of the tools at the Weather Service that we use to, we tried to look at flash flooding that's going on. And I won't go too heavy into the details here with what's going on in these different images. But basically we're looking at different, what they're called hydrologic models. And we're trying to get an idea of if there's going to be, like if rain's happening, if we're going to be getting flooding. But one of the bigger ones to point out here is probably the one on the bottom right, which is looking at the amount of soil moisture in the ground layer. And as you can see, as time goes on in this loop, you see that soil moisture from being relatively dry gets pretty moist as time goes on in these images. But this is one of the tool sets that we use when we're trying to decide if we're going to issue flash flood warnings or those kinds of things. And in this case, usually we look at the bottom left and the top right, especially in these kind of scenarios where the ground's not already saturated. And as you can see, there really wasn't too much of a signal on it. And then one of the other things I should point out about this is that what this comes from, because it's going to come up a little later, we're looking at multiple radars putting precipitation amounts together, and it that's how we generate these kinds of maps. So it's not just from the Boston radar, but it's also from it's also going to be from the Brookhaven radar, and even if the Albany radar has got some things to add to it, it may even add some information into this area. And if you want to go to the next slide, Joe. So as Frank had said, we did put out a flood warning for Nantucket and Martha's Vineyard. I think he said it was at 10 a.m., but it was until as you can see here, 1:30 p.m. For the heavy rainfall, as Frank had kind of alluded to. And then here is a list of some of the rainfall reports that we got, or flooding reports, and you'll see a little later there's a more detailed information of what specific information we had on the islands. And then the one thing Frank and we were kind of alluding to earlier, there was that tight gradients, even in the forecast models of, where there could be heavy precipitation to no precipitation. And as this map kind of points out here, you can see how sharp of a cutoff there is from far southern portions of southern New England to the Mass Pike. There's really not much rainfall in the north of the Mass Pike, whereas once you get to the further south, we've got the heavier precipitation, again, with most of it concentrated over Cape Cod and the islands. And as you can see on the right-hand side, that's kind of got your different scales of how how much precipitation occurred. And at least on this analysis, you got a couple pixels right on the island between 2.5 to 3 inches. And actually over the ocean, you can see that there's one that's estimating from 3 to 4 inches of rainfall. So we do take in reports from various different sources. And this one here would be from the CoCoRaHS observers, which is something that if you're interested in, anybody can sign up and join this. But just to look at the map here, you could see across Nantucket and Martha's Vineyard, we had rainfall amounts anywhere from 2.5 to almost 4 inches of rainfall, depending on the location. And I think that value, that 1.21 inches, I think the person, they put a remark that I think they fell asleep or something like that. So that's probably a little bit low. But you can even look, like if you go a little bit further north up towards Falmouth, I mean, that you have rainfall amounts even up there anywhere from 1 inch to 2 inches of rain. And again, just kind of honing in, you could see all across southern New England, but various rainfall amounts, again, with the heaviest across Cape Cod, the islands, but especially the islands, but really low rainfall amounts as you go north. And again, just to kind of hit home again, it is great to have this rainfall information, and it is something that we look at in the forecast office every day. It's really, really useful information having those ground reports, because we can't only rely on our radar to figure out what's going on, because sometimes it's not the best at estimating what's going on, which we'll see a little later on here. So here's a list of on the left-hand side, we've got what we call a public information statement, and it's just a list of the rainfall amounts, and this is specifically honing in on Barnstable, Dukes, and Nantucket County in Massachusetts. And as you can see, in Barnstable, we had a couple reports of, like we alluded to in the CoCoRaHS, of anywhere from 1.25 inches to 1.5 inches of rainfall. But again, with the highest amounts over Martha's Vineyard and Nantucket, where we had anywhere from 2.25 to 4 inches of rainfall in some spots. Although again, those are the reports that we had at that time at 8:30. And then on the right-hand side, we had showed that image earlier, highlighting those different points where there were flood reports. This is just a list of those specific flood reports across that we had sent out, again being concentrated on Martha's Vineyard and Nantucket. So here is an image that was passed along to us from the Oaks, or that we had grabbed from the Oaks Bluff Police Department's Facebook page. And as you can see, at the intersection of Kennebec, Narragansett Circuit, and Oaks Bluff, that there was water ponding on the roadway. So definitely some flooding going on here. And then this is another flooding photo that we had in Vineyards Haven. And then this is at the Five Corners, and this was courtesy of the Vineyard Gazette. So as you can see, water on the roadway, and people driving through the water. So on this slide here, we're as I kind of alluded to with those rainfall reports that we got from our observers, they were giving us much higher totals than what the radar that we were using, and even what the multiple radar sensor were estimating, especially early in the events. And to kind of get into, trying to not get too into it, but we use different reflectivity. So like the typical radar images that you see, we use that and we correlate it to how heavy the precipitation is. And that changes at different times of the year. So in this, so initially when we had started this event, it was set up for more of what you would see in like a wintertime scenario. And that's usually not, it doesn't do very well in these kind of situations when warm rain processes are going on, or you have high precipitable water content air masses. So during the event, we had switched to a mode which we call convective, which is more suitable for the summertime or spring and summertime. And that helped improved estimates, but it was still underestimated. That's probably likely due, again, to usually even the convective processes, when you have high precipitable water air masses, that you can tend to, they tend to even overproduce even when something is designed for it, at least at this point in time. So we kind of started off in a situation where it was, we were starting off on the bat with the right rainfall relationship, but we switched over to a better one. And again, we did see that I didn't point it out on the previous slide, but the hydrophobic model, one of the hydrologic models, did show a strong response. But what essentially happens in those scenarios, it assumes that water, if it's falling, it's automatically just going to run off and go into or go onto roadways and that kind of thing. So it usually overestimates the scenario, and it's better for different situations, but this wouldn't have been one of them. And I think with that, that's all that we have, unless you have any questions. And I know Joe will have to take over here.
Okay. Yeah. Thank you, Bill. And Frank and Rodney, it's a great presentation. Hopefully not too technical, but we try to water it down, no pun intended, as best we can. Let's see. Feel free to answer your questions in the chat. Sounds like some of the audio might have had some issues, so we apologize for that. Here's a question from Michael. Does NWS have a document that explains acronyms such as PWAT in a format that a non-scientist can learn about meteorology? And Hayden, I believe there's online, the nws.noaa.gov website has a kind of glossary of terms, if I recall.
Yeah, it does. And actually, there's certain words that if people that read our area forecast discussions, if you go on our website, I believe there'll be certain words like that we'll use. Sometimes they'll appear in blue, and you can click on that and it will give you a definition. I think that still occurs on our website.
Yeah, there are links in the forecast discussion. I'll explain some of the technical terms. Another question from John. How can I track PWAT plumes as they track north? Who wants that one?
I could take that, Joe. One of we had showed it earlier, looking at the Storm Prediction Center's what they call the meso analysis page, and that's actually, they have I would say that would be the best page to look at, looking for these kind of plumes in like real time. And the link to that would be spc.noaa.gov, and then when you're on that web page, you'll see at the one of the top things, it'll say meso analysis, and then you can kind of hone in on parts of the country you want to look at.
Yeah, and you can also look at the GOES satellite data. You can just Google GOES scene. There's a number of sites that provide that data. If you look at some of the moisture plumes, you'll see the plumes coming up in the Gulf of Mexico or the Caribbean. Okay, question from Benjamin. Is flooding worse if it happens near the ocean? That's our friend Ben from yesterday.
Yeah, I can take that, Joe. it depends on obviously what roadway you're on. But from a perspective, flooding is flooding, and it really doesn't matter if you're talking about coastal flooding or freshwater flooding. Depending on your location, the depth of the water. Obviously, if there's water flow, it can be extremely dangerous. It's dangerous. So it doesn't really necessarily matter what the cause of it is.
Okay, thanks, Aiden. Any other questions? All right, we're seeing none. We're going to wrap up this webinar, and in the future, we will schedule webinars for event reviews that we complete as we go through the summer. We're also thinking of having some webinars on like Weather 101, maybe even a forecasting webinar. So stay tuned to the website and social media, and we'll advertise those as we schedule them. So thank you again, everybody, for attending. Again, this will be in our YouTube channel either later tonight or tomorrow, and we'll talk to you soon. Thank you.